welcome to the second part of tutorial chapter 10, and in this chapter we will learn about an extension version of the binomial regression, which is the Poisson regression. Binomial models are appropriate when the outcome is a count from 0 to a known upper bound, which is the n trial, and when a binomial distribution has small probability of the event p and a very large number of n trials, then it turns out to be a special shape, the Poisson distribution. So to build a generalized linear model with this kind of likelihood, we need another link function. Because the parameters in a Poisson regression, the lambda means how many times the event will happen in a certain time interval. So we can use the log transformation as our link function to convert positive real numbers to the whole real numbers. The data we will work with are counts of unique tool types for 10 historical ocean societies. So we can see that this total tools column is our y. The predictors we will use will be the population and the contact rate for each island. And what are the relationship between these predictors and our y? So the author makes three assumptions for us. Firstly, the number of tools will increase with the log of the population size, and then the number of tools will be higher if the island will have higher contact rate, and then the interaction of contact rate and the number of population will also interact. Based on the above assumption, we can write down our Poisson regression model like this. So log lambda will be equal to alpha plus beta times log population, and we will have different alpha and different beta for high contact rate and low contact rate. So you can see index coding here. We also need some preprocessing for our data. So I standardized the log population using a scale function, and then I used the as integer function to make the contact high low to integer index. Created a new data frame called a test k-line data frame. Because we have very few data points, like we have only 10 societies in our data set, and the population in this data set has a very wide range. So I need to create some fake data points to make our posterior plot a smooth line. Code for test k-line data frame is a little bit complicated. Let me explain what I was doing here. Firstly, I make the fake standardized population from negative 1.5 to positive 2.5. I choose these two values because this is the maximum and minimum values in our training data. And then I separate, I put 99 points in these two values, and then I add another very small number value, negative 5, to have a point like an island with 0 population. And then we need to convert this standardized population into the original scale. So I call the unscale function and provide the original scaled training data into the unscale function. So it will apply the transformation based on the original scale. And then don't forget, we have a log on our training data. So we need to use the exponential function to convert the values into the original value. If you are not confident about the scale and unscale function in here, you can check this line of code. We will see that, okay, we successfully convert the 10, 20, 30 vector from a standardized result to the original result using exactly the same code here. We also need to visualize our prior to make sure it's reasonable. A log transformation will make all the negative numbers to be in the range of 0 to 1 on the outcome scale. So if we use a flat normal prior like a normal 0-10 on alpha, the output lambda will concentrate between 0 and 1 while having a very long tail on the right, just like the black line here. On the other hand, the prior be something like normal 3, 0.5, which has a mean of 20 at the outcome scale, will be relatively uniform across all the values of lambda. And the author suggests us to use normal 0, 0.2 as the prior distribution for the beta. And let's plot some prior prediction regression line for our Poisson regression model. I draw 100 samples from the prior distribution of alpha and beta, and then I use the fake standardized population I just created in the test k-line data frame as our testing data. And I want to plot the Poisson regression line on both log scale and the original scale. So I use a for loop to loop over the 100 samples I draw in prior alpha and prior beta. And then the prediction value will be exponential of prior alpha plus prior beta times the x. Plotting the result on log scale is very simple. You just need to use a geometric line with aesthetic equal to standardized population and the prediction. However, if we want to plot the result on the original x scale, we again need to use the unscale function and exponential function to convert the standardized population to the original scale. So this is the code we use to create a test k-line data. From these two plots, we can say that our prior distribution is reasonable because we want to have a regularized prior, so that most of our prior prediction regression lines should be horizontal lines, suggesting weak relationship between the predictor and the output. Okay, now let's look at our stand code. And this time the model code is a little bit different because we have one training data and one testing data. So in the data part, the training data is just like what we did before. We declare the length of our training data, declare the level of categorical variable, and this is our y, and these two lines are our x. And for our testing data, we also need to declare length of the testing data, and then we only have the data for the predictors. And we don't need to declare the level of categorical variable again because they are the same. And also we don't have the real y value, so we don't need a test tool column either. The parameters part, nothing new. We have alpha for high contact rate and low contact rate, and beta, 2 beta as well. In the transform parameters block, in the logistic regression problem, we have inverse logic function here. And you may think, okay, we may need an inverse log function. But actually, the inverse log function is just the exponential function. So this is the exponential function, and the linear relationship is alpha plus beta times population. And this population is log population. You can see we have index coding for both alpha and beta. In the model code, it's just like what we did before, but now we have the sampling statement Poisson lambda, and this lambda was calculated in the transform parameters. The new things are in the generated quantities block. So firstly, we not only need the log likelihood, we also need to calculate the prediction lambda. So we declare a real vector of length test n of prediction lambda. And in the first part, we calculate the log likelihood just like what we did previously, but now we have the Poisson LPMF function, and we compare the output, the real training output tool I with our predicted lambda I, and to see the likelihood value. And we make the predictions here. So we need to make predictions for length test n. So the for loop is from 1 to test n. The prediction lambda is calculated here, and using actually the same function as the same linear relationship as what we did in transform parameters, but now we replace the contact and population predictor with the testing data, test contact and testing population. And then let's look at the second model. So the author, as an expert in anthropology, suggests us to use a more scientific model. So from past research, we know that tool innovation is proportional to the population size, but with diminishing returns. Besides, as the number of tools becomes larger, some of them will be disappeared because we may have some duplicated tools, and as time goes by, people will only use the advanced tool. So the scientific model will be like this. Lambda will equal to alpha times p with beta power of beta divided by gamma. So alpha will be something like a constant rate of tool innovation, and p will be the population, and beta is like the diminishing returns. So the beta value will lie in the range of 0 to 1, with the smaller beta value means the stronger diminishing return effect, and the gamma will be the rate of tool loss. Let's look at the stand code for the scientific model. So the data part is the same as our math model, and the parameters part, now we have alpha, beta, gamma, and because lambda is positive, so the value for alpha, beta, and gamma must be positive as well, and we have 2 levels of alpha and 2 levels of beta, and this is the assumption by the author. So in the transform parameters part, you can see that now there's no exponential transformation in the regression line, in the regression equation. We just need to set lambda equal to alpha times the population with power of beta and divided by gamma, and with the index coding in alpha and beta. The model part is the same as well, but the prior distribution is different because now alpha, beta, and gamma are all positive values. So we set the priors. These prior distributions only have positive values. In the geometric quantities block, again, we have one for loop for the training data to calculate the log likelihood, and the second for loop to calculate the prediction result on testing data. And then we can plot the posterior prediction of these two models for comparison. And firstly, let's do the math model prediction. As usual, we extract the output from our stem function, and now we extract the output for our testing data, the prediction lambda values, and then calculate the percentage interval and the prediction mean values. And we use the geometric line and geometric ribbon function to plot the prediction mean and the confidence interval. But notice that I add another aesthetic field equal to contact and the ggplot function here. So geometric line and geometric ribbon will inherit this aesthetic. So you can see there will be two lines in two colors, and one line for contact rate, high contact rate, and one line for low contact rate. However, if we want to plot the training data also on this graph, we need to set another data. The length for training data and the length for testing data are different, so we need to assign the data here again in the geometry point function, and the aesthetic function here also need to be updated, and the field aesthetic here need to be reassigned because the aesthetic we assign in the ggplot function is using the column of result 10.3.1, so the length didn't match the data here. With the above code, we will generate this graph, and now let's analyze the posterior prediction. The trend for tool innovation for societies with high contact rate is higher than that for societies with low contact rate when population size is small. However, the model allows the trend for high contact rate to be smaller when population size is higher. The problem occurs because we don't have any item with high population and high contact rate in our training data. So you will see the confidence interval for high contact rate islands prediction is very wide, and the math model has no guarantee that the trend for lambda will pass through the origin where the tool innovation equals 0 and the population size equals 0 as well. And then we can use the same code but replace the data with the result from scientific model to have the same plot. And you can see that the scientific model solved the two problems in math model. Now islands with high contact rate invents more tools than island with low contact rate, like in any population size. Besides, the two lines all cross the origin point with 0 tool and 0 population. Theoretically, a scientific model is more persuasive as well. If we use the rethinking compare function to compare the WLIC value of these two models, we can tell that scientific model performs better as well. In the last section of this tutorial, we will learn about exponential model, or you can call it survival analysis. If you remember your introductory statistics class, exponential distribution is closely related to Poisson distribution. Poisson distribution describes the count of occurrence of an event during a time period. On the other side, exponential distribution can describe the time difference between two occurrences of an event. So usually we'll use exponential distribution to answer the question like how long does it take for a certain thing to happen. Here, we will use a very interesting data set called Austin cats to answer the question if the color of the cat has impact on the adoption rate. Let's look at the data first. So we have the Y value, days to event, and there are different events. Some cats are transferred, some cats are adopted. We need to separate the adoption event from others. Also, we have the colors for different cats here, brown, teddy, blue, black, but we limited our investigation to only see the effect of black and non-black cats. The model for this problem will be a little bit complicated. We will need two likelihood functions for the cats being adopted and the rest of the cats. The cats being adopted is simple. They just follow an exponential distributions. However, for the other group, we can imagine that after 30 days, half of the cats are adopted. Then the probability of waiting 30 days and still not being adopted is 0.5. So 1 minus the cumulative distribution, or we can call this complementary cumulative distribution, CCDF, will give us the probability a cat is not adopted by the same number of days. You will notice that actually we only need one parameter, the lambda value in the exponential distribution, and we can model two different groups of cats. And this is the visualization of the cumulative probability of exponential distribution. So this area above the cumulative probability and below p equal to 1 is the CCDF, a complementary cumulative distribution. And then let's look at our STEM model. So the data part is very simple. In the parameters part, we want to estimate the lambda value for different in. Let's look at the model. The data part is very simple. In the parameters part, we have only one predictor, alpha. So one for black cat and another for non-black cat. In the transform parameters block, we didn't estimate lambda directly. Instead, we estimate the reciprocal of lambda, mu. That's because lambda means the time difference between two occurrences of the event, but mu will be how many times the thing will happen in a time interval. So setting a prior for mu will be easier for compared with setting a prior for lambda. In the for loop, it's the first time you see if else statement in STEM function, in STEM model. If cats are adopted, we need to use the exponential likelihood function. And for the rest of the cats, we need to use the complementary cumulative density function, CCDF. However, there is no built-in sampling statement like the exponential distribution in STEM. So we need to use the customized sampling statement like this. So we need to add the exponential LCCDF, which means a log complementary cumulative density function, into the target. So target is like an implicit variable, and it will store all the sampling statement in it, and STEM will perform a likelihood maximization for this target variable. Actually, the sampling statement we are so used to is the simplified version of the target function. In the generated quantities block, we make our predictions. However, here we do not make our predictions using the exponential distribution. Instead, we want to make the prediction for the proportion of cats left in the shelter for cats in different colors. So the for loop for I from 1 to 100 means from day 1 to day 100. And what are the proportion of the cats will be left in the shelter in these 100 days? So in the first day, both black cats and non-black cats have 100% left in the shelter. But after 50 days, maybe the black cats, 50% of the black cats are left. However, only 30% of the non-black cats are left in the shelter. So we want to make the prediction like that. So we should use the complementary cumulative density function to make a prediction. And in the posterior plot, we extract the samples for black cat prediction and non-black cat predictions separately, and then calculate the prediction mean and upper bound and lower bound for black cat and non-black cat separately as well. And in the final prediction plot, we draw the geometric line and geometric ribbon separately, and you will have a result like this. So you can see that in day 0, all the cats are left in the shelter, but after 50 days, like 27% of the non-black cats are left. However, like 35% of the black cats are still left. This is the end of the tutorial for the second part of chapter 10. I hope you enjoy watching these videos. The cat's adoption example is a little bit complicated, but the models we will use in future chapters will be even more complicated, I promise. But I will try my best to make you understand these models better. Let's take the challenge together.